Thank you so much for coming today. We are in Alpha Labs. So if you don't know us, we are a Web3 developer community. But us is not important for tonight. All you have to know is we have a night filled with ZKML. So to start, we'll have Dante from EZKL doing a demo on the spot. I pressured him into it. So we'll see how it goes. And then we'll have well, and Daniel from Modular. So you guys are all in this space. We are all developers here. Full stop. So this is going to be a very fun night for all of us. So hope you all enjoy. Thank you.
All right. So this is not my laptop. So that's part of the magic trick. All right, so I guess, okay, so I don't have any slides, but I thought what might be helpful is to like quickly explain what EZKL is, the best way to interface with it, and then you guys can like go off in the next few days and like break it and send bug reports to us and like we'll aspire to make it better. And I guess I'll end. Okay, so recently, like the team is fully remote, but we recently all got together in Boston and developed an end-to-end application leveraging our stack, just to like sort of showcase the sort of thing you can build and like how you can get all these pieces to fit together. And we're going to have a write-up like as a tutorial on what we've built exactly. I mentioned this earlier, but we need some volunteers to sing as part of the demo. So if anyone is feeling particularly adventurous and wants to sing and like showcase their singing voice, then yeah, step up.
Ask your AI.
Yeah.
Well,
Anna Rose.
well,
yeah.
not to like give too much away, but you're going to be singing to AI. Yeah. All right, so most of EZKL is like built in Rust, and it's leveraging Halo 2 to basically, you can compile like common deep learning formats like ONNX or TF-Lite into a bunch of Halo 2 circuits. So that's kind of what the Rust code we have does. But if you're going to be interfacing with this, like the easiest way to do that is probably through Python. And as of this morning, we have a TypeScript package. Very, very new, go break it as well. So if you want to get it set up like pretty quickly, you can just like open Google Colab and use their compute for free. You know, don't want to use your own computer. So we have a pip package, which is pretty handy. Oh yeah. All right. Please install. What? Yes. Enhance. All right. Cool. And that's it for the no. All right, it's installed. That's it. My job's done. All right. I don't actually, let's not do this because it creates very disgusting logs. So just need to import some things, but like the body of what's going to happen. So you can interface with the library through like Torch, TensorFlow, whatever exports to Onyx. Generally, like we've tested the most on PyTorch. So use that first and then move on to TensorFlow after. But the main way you're going to define a computational graph, which gets turned into a circuit, is through the Torch and then module interface, which is just like a simple way to define a computational graph. Let's start with this example, and then we can go back and I'll take like crowd suggestions for computational graphs, and we can all have fun as a group. All right, so that's how you define a computational graph. You can export it to Onyx. This is just some boilerplate stuff. And this is where we start to get into ZK territory. So we've aspired to like so basically we want like a ramp up in terms of like complexity, in terms of like, if you're not familiar with ZK, you can still use the library. But if you're also familiar with ZK, you can sort of like tweak it to your knowledge or to your needs. And I guess the main thing you'll be interfacing with is like defining what is public and what is private, or what is visible to the prover or the verifier, and that's done through this object, which is pyrun args. We also have a few other visibility arguments. So beyond like public and private, you can also say, I've pre-committed to like a hash of like my inputs or my model parameters and blah. And yeah, we do that. And you can also like encrypt stuff if that's something you're into. There's a few applications that ask for that. We use ZKML encryption, and that's another visibility option if you're interested. But for this case, let's have like the inputs be hashed, or I don't know. Okay, just to like, let's make this private. And then this should be public. Yeah. And then as part of like taking like a lot of the design complexity out of your hands, we have a function called calibrate settings, which is going to pick like the size of the circuit, the size of the SRS string you need to be able to like fit the model into a Halo 2 circuit. And yeah, you don't even have to know what a ZK is. So yeah, calibrates the settings file, blah, blah, blah. Fetches. So thankfully, our friends at PSE host a bunch of SRS strings on an S3 bucket. And this fetches the correct SRS string from you from S3. At some point, to like lessen the bandwidth load, we'll start hosting these. So PSE don't get murked with like a massive AWS bill. We have like a generate witness command, and then you can mock prove if you're like really paranoid, and then you can like set up your proving key and verifying key and then generate a proof and blah. That's kind of it. I don't really know how to set up Anvil in Colab. I know some folks have done it, but you can also like deploy like a solidity verifier. You can create it, deploy it, and then make calls to like verify proofs all within the same interface. So there's no context switching between like Python and Rust. Let's go back to the fun part, which is like defining the computational graph. We can do something crazy, like take this to the power squared, and then, I don't know, -5, and then call relu again. I don't know. Does anyone have ideas? All right. Okay, nobody has ideas.
We can just perceptron, the one from Jan Lepin from 1980 something.
Oh wow. Okay. Are you testing my historical knowledge? Or...
It's just
what is it? Is it a sigmoid?
Oh. And then dot linear plus relu.
Okay.
It's actually the easiest.
Or is it sigmoid? Or
Yeah, maybe.
I think it's sigmoid.
I thought it. I don't
Wait,
really
no.
know.
That's up to one to look at.
I think it's a sigmoid because they mainly used it for classification. All right, let's say it's like 48 by 2 or something.
Yeah.
And then where do we want to put the linear thing? Well, maybe we should get rid of the conv at that point.
I mean, you can just pick any perceptron Python tutorial and copy paste.
Well, we're doing this live though. All right, do the shapes make sense here? I think the shapes make sense here. I think this all makes sense. So this is a very weird perceptron. There's some things to the power squared. There's a -5, and there's 2 relus applied. Do we only want 1?
2 is better.
2 is better.
Two's
All right.
difficult.
2.
If you want to break the code, then
It's not, it's discretized.
Well,
Oh, so you have for the perceptron, actually, there are 2 parameters that define a linear function, W and B, slope and y-intercept. And the perceptron maps to 1 if it's greater than 0 and 0 if it's 0.
do you want greater than in there? Oh no, but that's just relu. Oh, so it is a
Not
relu.
I thought
Oh.
relu was
Oh, wait, what is-
Yes, really, it's just the positive part.
Yeah,
Yeah, no, this maps to one if greater than 0 and 0 if it's 0, so it's just binary.
Yeah.
all right. Okay, let's
The
come back
perception
to that.
just Categorize 1 and 0. It
Yeah.
doesn't do anything.
Okay. Okay, let's do this one first, and then let's come back to that.
Yeah.
Okay, so what is that? It's like 48 dimensional or whatever. What did we define it as? I think that's what we did. Cool. Kapow. That exports, boom, visibility. Let's hope this works. Pray to, oh yeah, okay, we're in business. Calibrating, da-da-da-da-da-da. Fetch the SRS. Thank you, PSE. Generate the witness, and then let's get straight to like setting stuff up and then proving. Kapow. And voila. All right, applause, please. Thank you. Thank you, thank you, thank you. All right. So yeah, you kind of get a sense for like what's possible. The way things work in the back end. So originally our first approach was literally to take one operation and then implement its equivalent in Halo 2, which is kind of tedious because there's like hundreds of Onyx potential operators and those sorts of things. So what happens in the back end is that like all of these hundreds of operations get reduced to a set of like 20 or 30, and using those 20 or 30 operations, you can then reconstruct the hundreds of operations that you have available in like deep learning libraries. And that's kind of how we improved a lot of our coverage for like operations and those sorts of things. Cool. Do you guys want to play around with the graph more, or do you want to see, do you want, actually, do you guys want to sing now? All right, so.
One more question.
All right, so one of our developers went like completely overboard on the assets. So there's like 1 gig of assets. Oh, we're all right, sweet. Okay, so this is what we came up with as a team in Boston. Yes, well, you know, Boston suburbs, you're kind of locked in a house. You're gonna come up with some weird shit. So yeah, so the idea was to create like a really simple low stakes application that leverages every part of the stack, and that people can then fork to then build applications on top of. And so the crux of the idea is that you sing into this interface. Behind the scenes, there's a ZKML model, which like ranks you.
That's the model value quality.
Well, it's karaoke.
Yeah, it's basically, it's on-chain karaoke, because then you can take the proof
Oh, got it.
and submit it on chain,
Jeez.
and the verifier then there's then a permanent proof of your score.
Like, what's the metric of like average squared error or something?
Well, I don't think I can tell you.
Yeah,
Yeah.
yeah.
Well, okay, I'll tell you. So the way we did it is there's actually a bunch of like standardized like emotion labeled data sets on Kaggle where people are singing or speaking with like different intonations. It's like, oh, pleasantly surprised or angry or those sorts of things. And then we basically trained a regression model to really, really like one of those emotions, which I won't say which one. And then, yeah, that's kind of the gist of it. So yeah, kind of a fun little application.
If someone is very good at singing metal, it wouldn't work.
It actually doesn't matter if you're good or not. That's sort of the trick.
It matters if you're angry enough. Correct.
Right, like anger is not the emotion that we optimize.
I think
for.
that.
Well, actually, we might be optimizing for anger. All right. Blah, blah, blah. Is this gonna work? All right, we are connected. Sweet. This is the future, guys. This is what we're all building towards.
Yes.
Right?
Yes,
Yeah.
yes, yes, yes.
La 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 la.
I think we spent more time doing the animation.
All right, do I have to approve this? Oh, yeah. All right, confirming on my app. And you can share it on LinkedIn.
What the heck?
You can share the results on LinkedIn for your employer to see. So there you have it. We're going to be releasing end-to-end tutorial on how to build something like this in terms of like the proving infrastructure that goes behind it. This leverages like the new TypeScript library that we released this morning. We also go through how we develop the model in Python and all sorts of things. So yeah, that's kind of it. That's my improvised presentation. Yeah.
Wait, so how well?
Yeah, what's the score then?
The score one is.
Yeah, I'm
Oh.
curious.
It's 10. It likes it.
Yeah, it's 10. Well, actually, oh yeah. Well, S is 7.
It
Yeah.
looks like the. Wait, why don't
It's out
the
of 10.
score compares to the rank. 'Cause
Is I better? Or?
it does.
I know SSS, SS, A, but I don't know S.
Yeah, and Y is, yeah.
Don't ask me. It's the model. It's not me.
Score should be like, probably like, should be like a linear output, so.
Well, it also spells sax, which is
Yeah.
short for saxophone.
Like, why is it all?
No.
Why is like a output, why it's like. None of it makes any sense.
It's okay.
I don't think it's supposed to be. Is it trained on your like?
No. Well,
That's fine.
yeah, I put a few samples, which I upweighted heavily, for sure. That's not part of the tutorial, though. All right, there you have it, folks.
We mentioned algomal encryption. Does that mean you can encrypt the feature vector prior to creating the demo model? And if that's the case, does the circuit itself decrypt it to do the evaluation?
No, so basically the output of the circuit, one of the outputs of the circuit is then going to be the encrypted values, but the model is going to operate on the unencrypted values. So basically the idea is you can do something like, hey, I have a bunch of encrypted stuff, and here's an evaluation of one of its properties by an ML model.
I see.
So let's say you have like an encrypted image or something, and you want to prove that it's like a picture of a fan or something. The model can then be like, this encrypted thing is definitely a picture of a fan. You can make that clean.
But you have to provide the image to the model, and then the circuit itself basically verify that the encryption is done properly.
Yes,
I got
so
it.
that's part of the circuit.
Oh,
Yeah.
shit. Okay.
Yeah.